Dear viewers, you are my greatest inspiration. You have supported me all these years. Your kind words of appreciation motivate me to keep making more videos. Welcome to my quantum physics video lesson series. This video series is a full package, or information bank. The viewers are advised and encouraged to watch each and every video lesson in this video series, in order to perceive the background concept. These 7 distinct video lesson episodes are a thought-provoking journey through the subatomic world. This particular video here offers an exclusive lecture on the key subtopic, diffraction versus interference. For the first time and the one and only time in the entire YouTube, this video lesson is presenting a unique, comprehensive, profound, pictorial and extensive comparative analyses of wave diffraction and interference, in connection with wave-particle duality. How these two phenomena are interrelated, as well as whether they are exclusive or co-existent, have been scrupulously explored. Light waves are electromagnetic waves. Such waves exert electric and magnetic forces. The displacement of the wave at a point indicates the direction and relative magnitude of the force. Conventional technical definitions are in quotation marks. Italian mathematician and physicist Francesco Maria Grimaldi is credited as the first to record accurate observations of light diffraction in the 1660s. Grimaldi's work on diffraction was published in 1665. We are going to study cases of point sources, broad sources, spherical and disk obstacles, and coin experiments. The shadow of the spherical object is not completely dark. Let's see how light invades shadow. Please observe how the waves traverse around the boulders and the duck, as well as intersect each other, forming various wave patterns. Now, replace the boulder and the duck with a coin or steel bead, and then water with light. If we observe a shadow carefully, we will notice that it's somewhat blurry at the edges. According to Huygens' principle, each point on the rim of the sphere or coin behaves as a source of secondary wavelets, which illuminate the central region of the shadow.
Now, replace the boulder and the duck with an open gate, a single-slit aperture, and then water with light.
Huygens' principle of secondary wavelets, proposed by the Dutch mathematician, physicist, and astronomer, Christian Huygens, has been immensely practicable over several decades and centuries, since 1690, for studying various optical phenomena. As stated in Huygens' principle, each point on a wavefront emits a semicircular wavelet.
Let's say, an aperture can be regarded as an open gate within a barrier or obstacle. As stated in Huygens' principle, when light encounters the barrier and passes through an aperture, each and every point of the light wave within the aperture can be viewed as creating a new spherical wavefront, propagating outwards from the aperture. The edges of the wavefront bend after passing across the opening. The amount of bending is more pronounced for narrow openings. This is consistent with the fact that wave characteristics are most distinct for interactions with objects comparable in dimension to the wavelength.
The alternative blue and teal lines represent the wave maxima and minima. The wavelength is denoted by the distance between the blue lines.
When light encounters obstacles or apertures, the dimension of the obstacles or apertures, relative to the wavelength, is crucial. You can see how it appears with the aperture width greater than the wavelength. In case of single-slit diffraction, one is basically splitting up the slit into an infinite number of infinitely small slits, right next to each other, and analyzing the resultant overlap pattern. Wavelet pairs destructively interfere, creating the dark minima on either side. Whereas, wavelet pairs constructively interfere at the center line. As you see on the left-hand side, if we increase the width d, the angle theta of the first minimum decreases, resulting in a narrower central band. Whereas, with narrower slit width, the angle theta increases, giving a wider central band, as illustrated on the right-hand side. The dashed lines in bright pink color show the path difference, hence the phase difference, between the light waves emerging from the two edges of the slit. A narrower slit on the left-hand side, and a wider slit on the right-hand side. You can see which part of one wave matches with which part of the other, depending on the slit width. Let's find a way to visualize the nature of single-slit diffraction more clearly. Shall we? by Huygens' principle, we can consider the wide slit to consist of an infinite number of elements or point sources, shown by yellow dots. Rays 1 and 2, shown in green, arrive in phase, and experience constructive interference. Now, let's look at the other element pairs. Rays 3 and 4, shown in violet, arrive 180 degrees out of phase. Now, tell me the names of the optical phenomena that involve bending of light. Wave interference is the phenomenon that occurs when two waves meet while traveling along the same medium. Light waves interfere when they occupy the same region of space at the same time. Here, let's study two pulses of the same amplitude and shape of sine wave, traveling in different directions along the same medium, shown in blue and green color. As they approach each other and eventually overlap, the sine pulse, shown in red dotted line, would be the resulting shape of the medium. Okay, alright, so now, how to achieve sustained or well-defined and observable interference pattern. Constructive wave interference occurs when waves interfere with each other crest to crest, that is to say, peak to peak, and consequently trough to trough, that is to say, valley to valley, and hence the waves are exactly in phase. This amplifies the resultant wave. Destructive wave interference occurs when waves interfere with each other crest to trough, which is, peak to valley, and are consequently out of phase. For equal amplitudes, this cancels each other out. For each approaching pair of pulses that have the same direction and magnitude, the resultant wave of the two interfering waves retains the same direction and doubles its magnitude, whereas, for each approaching pair of pulses that have the opposite direction and magnitude, the resultant wave ends up with zero magnitude. Identical waves in phase, that is to say, the peaks and troughs are lined up on both, cause constructive interference. The resultant wave has double amplitude. Identical waves in antiphase, that is to say, the peaks of one are lined up with the troughs of the other, cause destructive interference. The resultant wave has no light. Interfering waves of equal amplitudes are not a requirement for destructive interference to occur. In this example of destructive interference, two pulses of unequal amplitudes do not lead to complete cancellation. The sine pulse shown in red dotted line is the resultant that survived.
Well, perhaps destructive is not the correct expression after all. Right?
We are going to study cases of twin-point sources and double-slit experiments. In Young's double-slit experiment, light is sent through two vertical slits, and is diffracted into a pattern of vertical lines, spread out horizontally. In order to perform this experiment, he generated two coherent light sources, using diffracted light from a single slit. Please note that without diffraction and interference, the light would simply make two lines on the screen. Which is not the case. In Thomas Young's brilliant double-slit experiment, the central region of the fringe system is brightly lit. If light travels in a straight line, the central region should appear dark instead, which is the shadow of the space between the two slits. Which is not the case. The objective of Thomas Young's double-slit experiment was to verify the wave nature of light, as well as to demonstrate the theory and principle of interference, and the concept behind diffraction. Anatomy of double-slit interference. Each slit is at a different distance from a given point on the screen, indicated by red circle. Each point on the screen has a different distance to each slit. Different number of wavelengths fit in those two paths. If the two path lengths differ by half a wavelength, the waves would interfere destructively, whereas, if the path length differs by a whole wavelength, the waves interfere constructively. Here you see graphical plot of intensity, as a function of angle of deviation, with respect to the central position. single-slit envelope, is now split into a number of discrete bands, with varying intensities. Please note the color code. Single-slit pattern is indicated by royal blue line. Twin source pattern is indicated by violet lines. And the double-slit pattern is denoted by scarlet red line. When it comes to diffraction versus interference, students frequently ask, what are the differences, and what are the similarities? So, we would rather call it correlation or comparison. Richard Feynman is widely regarded as the most brilliant and iconic figure in physics for his work on the theory of light-matter interaction, dealing with the enthralling perception of the nature of waves and particles. Richard Feynman's historic quote, "No one has ever been able to define the difference between interference and diffraction satisfactorily. It is just a question of usage, and there is no specific important physical difference between them. The best we can do is, roughly speaking, to say that when there are only a few sources, say 2, interfering, then the result is usually called interference, but if there is a large number of them, it seems that the word diffraction is more often used. Interference and diffraction are the phenomena that distinguish waves from particles. Waves interfere and diffract. Particles do not. Such phenomenon cannot be explained with a strictly particle view of light. Thin film interference occurs without diffraction. As the light beam experiences 180 degrees phase shift at each reflection, the emergent beams shown in violet and green colors happen to be in phase, indicated by red dotted lines. By the way, the wave colors used here have nothing to do with wavelength. There is a simpler way to comprehend the concept. Diffraction may lead to interferences. Interferences do not always arise from diffraction. It's more like all alkalis are bases, but all bases are not alkali. Ready lecture notes and study materials are available on request. Please use the comment section below for further academic discussions. Viewers' suggestions and ideas of new video lesson topics are gratefully appreciated. Stay tuned for more uploads. Please remember to like, subscribe, share.